knowing her very well. Just let us have a brief introduction about her. Mrs. Mansi, Madam, I just request you to please turn on your camera for a while. Yes, thank you very much. Okay. Mrs. Mansi Masrani holds the master's degree in VLSI Design from Nirma University. She is having experience of 6 years plus and the field of physical design engineering at the Intel Bangalore. She has started her career as an intern in the memory compiler team, and then later she has worked with different teams like for as an FEV, that is a functional equivalence check, as POC across teams and IPs. She is currently working as an FEV lead for the teams, along with handling the physical design for the latest generation of CPUs. And her specialization belongs to the synthesis, FEV, design for test, place and route, and reliability verification, different things. So, on the behalf of Government Engineering College, Rajkot, Electronics and Communication Department, I, Dr. Dhaval Bhojani, heartily welcome you, and I am handing over you to the session. Thank you very much.
Sure, sir. Thank you so much, sir. Okay, so I shall start my presentation now. I'm gonna disconnect my video and start my presentation so that the bandwidth doesn't overtake. Okay. Let me know once you can see my screen. Is it visible to all?
Yes, it is visible.
Okay, so let's start. So I believe we have gone through synthesis one day before, and today there was a second session where we studied floor plan and placement, and that's what the VLSI flow consists of, which starts with RTL verification. RTL verification, synthesis, floor plan and placement, and today is where we will talk about clock and route. Okay, so the first thing is the clock. So now the main goal of doing the clock tree synthesis for any design is, till now, until your placement is done, the clock reaching to your flops are all logical. The connections which you see till the placement is done in the tool is all logical. The clocks are ideal, the delays are ideal, and it's not the real time delays which clock tree synthesis would show. But once you have to go through the clock tree synthesis, which we will actually route the clock tree. The clock nets will be routed along with the buffers, and it will reach to all the flops. So the main goal over here is to route the clock tree properly. Now, let's start with the very first basic question. Why do we need to route clock before any other signals in the design? Can anybody tell me? I can do that like later in the stage where all my signals are routed, and now I know that, okay, only clock is pending, let me route clock now. Will it be feasible enough? Okay, so the answer is no. We need to route the clock before any signals in the design, because we need to make sure that clock gets the maximum flexibility inside the block. You need to have open area. So to make sure that it has enough area to choose the best routing possible for the clock with the minimum delay. Normally, I believe when you have gone through the floor plan and placement session, you will have come to know that the very first thing which we plan is power grid. The power supply grid is planned the very first, and those take the topmost layer of the design. Let's say your design has metal layers up to 14, 13, 12, anything. Then the first two layers, let's say I have my design up till metal 12. Then the first two layers, metal 12 and metal 11, will be gone as a power grid. Now, after that, the metal 10 is where we start routing our clock. So the clock will take almost 2-3 layers because it is a huge part of the design. It takes up 30% of the area. So mostly it will take 3-4 layers, at least 3 layers. So M10, M9, M8 will be taken over by clock, and from there we will start the signal routing M7 to the M1 or M2 pins. Okay. Now we also route clock before any other signals in the design because we need to make sure that it has minimum delay. The clock signals shouldn't be much faster or slow so that the timing aspect of the design is broken. So we need to make sure of that. The third reason is power. To make sure that it doesn't consume more power, because clock is 30% of the design, so it will consume a lot of power. Clock cells are itself very huge in area. They are very power hungry. So to balance all the power targets, we will need to make sure that we route the clock before, optimize it properly, and then route the other signals. And the final thing is signal integrity, where we will save the signals from the variations and noise. We will come to know in the later part of the design how clock is so sensitive to noise, and we have to save it, from that, because once the signals come into picture, the clock will have a lot of noise on it, and if the clock is disturbed, the whole design is disturbed. Let's keep this session very interactive. You can ask me a question at any point of time so that I know that you are listening well. Just give me 1 second, I'll drink water. If you look at any clock in the design, you'll see few of the parameters which are inherently there existing for the clock. These are actually the variations for clock, but they are so inherent for the clock signals that we actually call them parameters. One of them is skew. Skew is what? That if you see this diagram, the clock reaching over here, this flop, and the clock reaching at this flop can also have differences in arrival times of clock. There cannot be two flops at which both the clocks arrive at the same point of time. This even the little bit difference will be there because it will have variations. It will have variations on net, it will have variations on buffer. So this difference in clock arrival is called skew. So here if you see, the clock edge at one register is arriving at 0 PS. For the second register, the clock is arriving at 2 PS. This is called skew. The skew over here is 2 PS. Now what is global skew and what is local skew? So the global skew is difference between the earliest clock in the design and the latest clock in the design. So let's say over here, the earliest clock will be probably here, here, or here, and the latest clock will be here. Though the color are different, which shows that these are all differently balanced for the skew. Let's say here I'm trying to balance my skew at 10 PS. Here I'm trying to balance my skew at 12 PS. Then, and here it's 20 PS, here it's 30 PS. So the difference between the least skew and the maximum skew is global skew. But when we talk about the local skew is the difference between clock in the same timing path. So here if you see, let's say I have a timing branch from this flop to this flop. Then the clock difference between those two flops is called a local skew. Just keep this in mind. We will be using this terminologies later also. The second variation or the parameter of the clock is called jitter. Jitter is what? Jitter is the difference between the clock period in different cycles. Even though we say that the clock is like square in shape, in reality it is not. In top of that, the clock period itself varies. So on the same clock, if one of the clock period cycle is 10 PS, the second one will be 12 PS, the third one will be 8 PS. The difference is not too huge like this, whatever I've shown here, but I've shown here to get know the feel that how it varies. This is called jitter. There is 2 PS of jitter over here, plus 2 PS, minus 2 PS of jitter over here. Can anybody tell me what will happen if the clock is like this? My whole design will be faster than 10 ps or slower than 10 ps? Can anybody answer me that? Okay, you guys are able to hear me, right? Am I audible?
Yes, Mansi, you are perfect.
Yeah, okay, sure. So here what happens is, yeah, so here what happens is, even though one of your clock period is 8 ps, you will feel that the design should be faster. The clock period became of 8 ps, but the whole design still has a clock period where you have 12 ps of clock period, which means that the whole design became 2 ps slower. And that is the reason we make sure that the jitter is as minimum as possible. We will see the source of the jitter and we will also see how to eliminate it. The third clock variation or parameter is transition. As I said, we feel that the clock signal is always squarish in shape and it's ideal, but in reality it does not. So it has a definite rise period, it has a definite slow fall time and all. So this is called the transition of the clock. The transition you can consider from 10% of the clock high value to 90% of the clock high value, or 20 to 80, but that all belongs into the rise time and fall time. Now the fourth parameter, clock parameter, is insertion delay. So what is insertion delay? Delay from the clock source to the registers. So let's say my PLL is outside the block. This is the block and my PLL is outside. So once the clock starts generating over here, maybe after 10 picoseconds it reaches over here, maybe after 30 picoseconds it reaches over here. So this 40 ps is the total insertion delay. Now it has two components. From clock source to the clock definition point for this block, the latency is called source latency, and after that whichever delay you see is called the network latency. Okay, now once we have talked about these parameters, let's see what are the effects of this variation on clock targets. Why are we even talking about these parameters? So now to tell you, because of this variation in clock, what happens is, as I said, anyways the clock structure is taking almost 30% of the part of the design. So it is anyway consuming huge power. Now any small variation is going to degrade the power consumption. So more power is used. And in the same case of area, clock generators, clock buffers, clock nets are anyway huge in area, and due to more variations you will be end up using more cells, more routing resources, and this will end up using more area. These two are the common targets which get affected, but the major one which get affected is timing. Okay, here let's see that everybody knows about launch clock, capture clock. We talked about last time in synthesis, right? I'm hoping everybody has gone through the links which I had provided, so I don't have to go through it again. Now here if you see, yes. So here if you see, this is the launch clock, okay, and this is my capture clock. So if you see over here, my capture clock is little bit delayed than the launch clock, and this is called the skew. Now here if you see, the capture clock is late than the launch clock, and this is what we called as positive skew. Now what will happen in case the clock has positive skew? It will relax the setup time and it will tighten the hold time. One second, sir, give me a minute. Somebody is at my door. Okay, I'm so sorry about that. So here if you see that at the capture clock, our setup time requirement is few seconds earlier than the capture edge comes. So now what happens is, now I've got this time more to meet my setup. So it actually relaxed my setup. But what happened to hold? Instead of measuring hold at this point. Now I'm measuring hold at this point, which is actually tightening my hold criteria. Because if you remember, after the capture age comes, my data should be holded for, let's say, some amount of time. Now my data should be holded till this amount of time, which is much more than the skew. So what will happen to the hold requirement? Instead of hold, now I will have a less time. Some skew time will be removed from there. So it will actually tighten my hold requirement. Now the reverse of this. In case of negative skew, my capture clock is coming earlier than the launch clock. What will happen over here? The reverse. It will tighten the setup. Why? Because instead of my data coming just before this age, now my data has to come much before this age, which is much stricter. The skew is already removed from the setup time. So it is much stricter. So it is tightening my setup, but it is relaxing my hold. My data should have come over here. Now, even if it comes here, here, anywhere, it's fine. So the hold is relaxed. These two slides, please go through again once we complete the session, because this will help you at all time how to get to know how the skew affects on the clock targets. This is the timing effect. Now, how will it affect on the signal integrity? So the signal integrity is nothing but that your signal should be ideal at all point of time, but in real time it doesn't. Clocks are way more susceptible to noise, and which can cause glitches on the clock signal, or at least even if it doesn't cause a glitch, it will at least slow down or speed up the clock propagation. Mind well, slowing down is always not the problem. Sometimes clock speeding up is also an issue. So you'll have to take care about that also. Now let's see how is that happening. So let's say there is this is V is victim. Victim is the one which is getting affected by the net with. Okay, this is clock signal. Now what happens is one of the aggressor is going from 0 to 1. Now if my victim is at constant 0, and because of the cross coupling between these two, what will happen is this was constant 0, this is going from 0 to 1. So suddenly my clock signal, we will see a jerk in that. It will see a big voltage pop up in the signal. This is called glitch. Now what will happen if at this period of time it reaches to the flop, instead of 0 it will register 1. Now the second part is when my victim is traversing from 1 to 0, and my aggressor, the one which is causing the noise, is going from 0 to 1. At that time what will happen is this aggressor will not let my victim come down from 1 to 0. It will try to hold it above. Now even if this is not called as a glitch, it will at least delay the signal, which is a major thing for clock. Okay, so this is signal integrity. Your whole signal has gone bad. It's not ideal anymore. So this is the effect of that variation on clock targets. The two difference you please remember, because whenever the victim is going to be constant, there is going to be a glitch. Whenever is victim transitioning from 1 to 0 or 0 to 1, there is going to be a delay. Now, where is this variations coming on? Why are we even talking about the variations on the clock? So the first thing from itself, the PLL, right, the phase lock loop, from where the clock itself is generated, from there itself the variation which comes into picture is jitter. There is no ideal phase lock loop which generates an ideal clock signal. It will always have some variations in clock period, and that is why the PLL itself is one of the sources of clock variations. Now the next clock variation part is the clock network. All the devices, the buffers which the clock tree goes through, right, they will also differ in the variation. And this variation comes from the fabrication, the size of the device, the VT type of the device, whether it's transitioning from 1 to 0 or 0 to 1, the signal changes, the temperature, everything comes into picture. And what happens at that point of time is, even if this device is same as this device, this two device will end up showing a difference in delay values. And this is called the clock variation. Okay. So each and every device will have their own variations. The nets between all the devices will have their own variations. No two metal layers will show the same ideal characteristics. They will also have different variations in their delay values. Now, the capacitive load also affects the clock. If one clock here, let's say, from here, if you see, this is the difference in the load. It has one more buffer over here, and then the flops come into picture. And this buffer sees two buffers directly and the load. So these two buffers capacitive load also are different, and the delay because of that would also be different. Now the capacitive coupling, which we talked about, right? The noise. Any two nets which are going side by side will have some capacitive charge effect between them, and which will result into noise, whether it's a glitch or a delay. In top of that, even the environment affects the temperature. Let's say this is my whole block. Now somehow the corner of this block is getting more heat because there is something over here, let's say AC to DC converter or something sitting beside over here, and which is discharging some heat. So this part will have more temperature, and because of that it's reacting differently. It is showing you some characteristics which are very different from this part. So that can also affect. The power supply can also affect, and the on-chip variation. This is a big topic which we can talk about it if the time permits. This is on-chip variation, which means even in the single silicon wafer, which is of 12 each size, right? No 2 centimeter by 2 centimeter part is gonna behave similarly. They're all different because even in the one wafer, every chip has the different variations on it because of the fabrication process. So all these are clock variation sources. Any questions till this point of time? Okay. Now let's say we understood one point, that my clock is not going to be ideal. We understood a point that there are everything on the clock structure is going to have its own variations. Even the clock generator is not going to give me a perfect clock. Now, how do I make sure that my clock tree, whatever is built, is actually perfect and working well for the design? So ideally, that is not going to happen, but we try to minimize this variation as much as possible. And in order to achieve this, what we do is we set some proper goals for clock tree, such as how to minimize skew and how to minimize the clock insertion delay. And to achieve those goals, we have to set some constraints, which are like max fan out, max transition, and max cap. I think we talked about these 3 points in synthesis, so I'm not going to re-talk about that. Let me know if you have some questions over there. Okay. So let's start with the, okay, can anybody tell me that minimizing skew is important, but why minimizing clock insertion delay is important? Can anybody tell me the difference? You guys are hearing me well, right? Okay, so my question is, I'm just going to repeat so that you get some logic in mind, that when there is a skew difference between two flops, let's say one flop is receiving clock at 0 ps, the second flop is receiving clock at 5 ps, this difference is going to affect my timing, power, and everything. But how the clock insertion delay from the source itself, if the clock is coming late, why do I care about it? It can come at 200 ps also at my design. Why do I even care? This is the question for you. If anybody gets to know the answer before we end up the session, let's talk about it, or else I'm gonna ask about it and we'll talk about it. Yes, anybody has the answer?
Yeah, ma'am. Narayan
Yeah, tell me.
Ma'am, its insertion delay will be the time which exactly will be required for the clock to reach from source to clock pin. So
Correct.
we need to take care when we are reaching to clock pin.
Correct. Let's say now that I am saying that from clock source, my PLL is outside of the design, and the source latency which I talked about, right? The source latency was from PLL to the clock port of the design. Even that insertion delay is important. Can you think about it? Why? Okay, so this has see, you have to think about it this way. Let's say if my clock is reaching in 50 ps instead of 100 or 200 ps, will it have more buffers or less buffers? I'm assuming you guys are hearing me. It will definitely have more set of buffers in that wire, right? A more long buffer tree or buffer chain, correct? So each device will have their own variation. So if clock is passing by 50 different buffers, and there is one more clock which is passing by 100 different buffers, which will have more variation? The one which has 100 buffers in the chain, and that will end up having more disturbed clock signal in the design. So you make sure that, okay, I want to reach my design from the PLL. Let's say my PLL is sitting over here. Okay, this is my whole SoC, system on chip. My block is this one. Okay, my PLL is sitting at the corner. Okay, what do I try? That I try to reach my clock from PLL to this block with minimum numbers of buffer required and the highest metal layer to make it free from the clock variation. Because if it is going through a long buffer chain, by the time it reaches over here in the design itself, the clock itself will have so much of disturbance in it that it's not going to work out well for my design. So that is why minimizing clock insertion delay is important. Now let's talk about the clock itself. We'll start with the stages. So one thing which we have to do before even starting CTS is validating the prerequisites. We'll talk about it. The second thing is defining what is clock, how many clocks do we have in the design, and the clock objects. Then setting the perfect rules for clock and the constraints. Then comes the actual CTS part, and then we will do the analysis. Okay, so these are the prerequisites. So can anybody tell me, when in the morning you went through the floor planning and placement session, what was the design which you expect at the end of it? After placement, what do you expect? Do you expect a clock in it? Okay. Do you expect at least standard cells in it? Is there a power grid in the place design, or it's not existing? Okay, I'm assuming you guys have gone through that session. So the design which comes after the placement should have a proper power grid, should have its macros placed, should have all the standard cell placed and legalized. What do you mean by legalizes? That the location of the cells are uh, kept, understanding in mind that it will have this much delay and this clock has to reach that cell in this much amount of time, though the clock is not routed yet and the location is fixed. While doing the CTS, if the cell itself moved, then there is no point doing CTS for that. So we have to fix the location of the cells. and the power grid is must required. Once you have that design pretty much ready for the clock tree CTS, then what we do is we identify the clock sources. What are the clock sources for the design? The clock port itself, from where, or if you have a PLL inside your design, then the output of the PLL is clock source. Then what you do is analyze congestion and timing. Can anybody tell me what is congestion? I really want to know if you guys have gone through the placement session properly. Have you guys talked? Did you guys talk about congestion over there? Okay. Can anybody just tell that what does the word congestion mean? Just in the layman language.
Madam, congestion means deadlock condition, madam.
Okay. Deadlock between what?
Here signals.
Correct. Correct. So that can be any signal. And the congestion can also exist in the cell area itself. So there are two types of things. You will have to take care of the cell density, that whether if there is a part of the design where there is a big chunk of cell sitting, okay, which is very congested in area, then the routing resources on top of that will be limited. So clock routing will be tough over there. So that is cell density and the pin density. Let's say I have two cells which has two input pins, one output pins. Then routing my clock to there is going to be easy. But what if the cells are bigger, a big adder, and there is a flop which has which is 8-bit flop in it. So I will have to route 8 clocks to that point. In that case, the clock routing is going to be tough. So we analyze these kind of congestion before starting clock tree synthesis, so that we know that we are not going to end up in a mess. Okay. The second thing is clock constraints we have to define properly. Max transition for clock, max capacitance for clock, and max fan out. And the finally what we give to clock tree CTS is that with all this, these are my targets: the skew number which we want to target and the latency number. Okay. Now defining clock and clock objects. What do we do is we define clock at certain clock port or the output of PLL. We name that clock, whatever CLK, clock A. If there are multiple PLLs and multiple clock ports, then we define them with a multiple names, and each of them should have different period. Because if there are two clocks with same period in it, then why do we have two clocks? Okay, so we'll have to define different period for clocks, and any design can have multiple clocks. Then we define clock start point, which is definitely a clock port or output PLL, and then we define endpoints. Now normally the endpoints are nothing but the clock pins of memories and registers, correct? But in this also we have to give a different kind of segregation so that the clock understands till what point it has to really build the clock and what all are the clock pins or the sync pins which it has to ignore. So the general endpoints are all called sync. Now sync pins are also defined as below. Stop pins. What are the stop pins is that these are the list of pins, these are the flops, and these are its clock pins till which I want to balance my clock tree. Those are called stop pins. What are ignore pins? That some of the pins or some of the flops till which I want my clock net to reach, but I don't want to balance it for skew because I'm not going to use that flop in my design at a later point of time. That's going to be a false path or something. So what do? We call it as a ignore pin. We'll tell the tool that please ignore this pin for skew balancing, but please buffer it. But then comes the exclude pin. What happens there? We tell the tool that please exclude this pin from clock tree synthesis. I don't even want this pin to be a part of clock tree. So it will just ignore that pin. Then there is through pin. What will happen is clock pins will be buffered and clock will be propagated forward through that pin. Can anybody tell me what kind of clock pins will be this? Does a flop clock pin can be a through pin? Does the clock like propagate forward through the Q pin of the flop? So let's say I'm going to draw something over here. Let's open my paint. Okay. This is my flop. Okay, this is my clock. This is my D pin, and this is my Q pin. And let's say this is D. This is clock. Can a clock pin of a flop can be a through pin? Through pin is something where we are telling the tool that after that pin also your clock should propagate. This is Q pin. What comes out over here? Does the clock come out or the data? Can anybody tell me that? Okay. Now I'm going to give you one more scenario. This is clock gate. Okay. And this is my enable pin. I'm just going to stop. And this is my clock pin. Okay. What comes out from here? This is clock. What comes out from here? You guys studied the gated clock structure? Okay, then we will talk about it. This is called gate because we are gating the clock whenever we want. This is something similar to AND gate. Okay, the output of this will be enable ended with clock. So what will happen over here is whenever my enable is 1, clock will pass. Whenever my enable is 0, nothing will pass. Okay, it will be 0. So this is the through pin. This is where we will tell the CTS that if you see a clock gate in the clock tree path, then I want to define that clock pin as through pin because my clock should propagate all its characteristics, period, transition, capacitance, everything should propagate along with that. That is called a through pin. Okay. Now float pin. Float pin is something which we define inside the memories, because for some memories we want to say that okay, my clock pin is anyway going to reach to this memory at 250 PS. So I want to tell my memory that please don't worry and start working before that. So that's why I want to set some delay over that pin, and which is called float pin. We will set maximum delay of 250 PS on that memory clock pin. Okay. Then other clock object is clock driver, which are nothing but buffers and inverters on the clock tree paths, which drive the clock from source to sink. Then specific clock cells, as I talked about clock gate and muxes. Can anybody tell me when do we use muxes? Clock gates we use for gating the clock. Why do we use muxes on the clock path? Does anybody know when the mux is used on the clock path? Okay, let's talk about it. I'm clearing this all out because this will help you understand the clock more. I'm just gonna draw a 2x1 mux over here. Okay. This is my actual clock of the design. Did you guys go through the DFT session? Okay. So here I'm gonna set this, and there is gonna be a select pin.
Yes, DFT session is covered.
Correct. So in that, I hope they would have gone through is whenever a flop is converted into scan flop, we put a mux over here, right? Where we decide that whether the data is coming or the test is coming. Same way, even the clock paths have muxes. And where does that come into picture? When we want to say whether our design is in functional mode or scan mode. In that case, what happens is, instead of SE, I should write test mode or func mode. Okay. Whenever my design is in test mode, the scan clock should pass as a main clock for the design, because my whole design is under test. I don't want my functional clock to be propagated. So at that time, I'm using this mux. And whenever my design is in func mode, the actual clock, okay, with which my whole design is going to be fabricated, that clock transfers. So these are two specific cells which we will use on the clock path. Okay, and then we define skew groups. As I told, we want not all flops to be perfectly balanced for skew, because that is ideally not possible. The last flop cannot have just 10 ps of clock delay. It will definitely have a much larger delay based on where it's sitting. So we will define small chunks of flops, and we will name it inside one skew group, that, and we will tell the clock that for these many flops, please balance the skew. The other group has some other number to be balanced. So these are the clock and clock objects. Okay. Now we will define clock rules and constraints. So the major rule for clock is routing them in the higher metal layer. Okay. Because it has the minimum RC value. So it has the minimum delay, and the clock is propagated faster. Now, for all the signal rules, right? For all the signal routing, what happens is we will use default metal layers, default metal width and all. But for clock, what we do is we actually change the metal layer width. We actually change the metal layer spacing. And those are not by default rules given by the technology. That's why we call them non-default rules. So there are some non-default routing rules in which clock nets are usually shielded with power or ground supply to nullify the effect of noise on them. We just saw, right, that if the aggressor is transitioning from 0 to 1, victim is transitioning from 1 to 0, there will be a small spike over here, and then there will be a delay, and the victim will settle down. But what if I am putting one, wire next to this clock net, which I'm tying to constant 0 or 1? What will happen is it will not let this clock net get coupled with this aggressor. It will get coupled with either constant 0 or constant 1. And what happens when we do that? It will just stabilize the signal, and it will not let any of the environmental other wire changes to affect to this clock signal. And what will happen is victim will ideally transition from 1 to 0 without any noise. So this is called clock non-default routing rule. Okay. The next non-default routing rule is clock nets are divided into 3 separate sets. Starting from the clock definition point to reaching to the clock pin of the flop, we divide them into 3 different sets. The first set is called root. What are the root nets? The first initial set of buffers, which we drive them in higher metal layers because it has the least delay. Then it has to come down to the cells, right? Usually standard cell pins are in either metal 1 or metal 2. My clock trees is built in metal 10, 8, 9 or something. So it has to come down to metal 1 or metal 2 to drive the clock pin of this flop. So as soon as it starts coming down, we call them internal nets of the clock tree. That can be a mix. It can have double width, it can have double spacing, it may not even have, based on whatever our constraints are and how much space do we have. And the last part is where it will see the clock pins of the flop. Here what we see is there is no control over the delay of the metal layers, because these metal layers are going to have the highest RC values. Okay, so there is no control of the delay. So now how do we save them from other issues? We actually shield them. The one thing which we learned over here, this is called shielding. We actually shield them over there. So the top nets we don't shield, we route them in higher level. This we can use a mix of it, higher metal layer, no higher metal layer, double width, double spacing, and shielding also if you want you can use, but this definitely needs shields. Okay. Now, what else can we do to save it? We use high drive strength buffers to be used for clock, which we call as clock buffer. We talked about this in synthesis. Can anybody tell me why high drive strength buffers? What will happen when you use a buffer which has W by L of 6 instead of W by L of 2? Will it be faster? Will it be slower? What will happen? Okay. Is everybody able to hear?
Yes, it is faster.
Yes. So then what happens is if we use high drive strength buffers for clock, the clock is faster, the variations are lower, and what happens is now instead of high drive strength normal buffer, we are going to end up using high drive strength clock buffer. And this is where we talked about it in our synthesis session, that the clock buffers have similar rise and fall time, which actually tries to make the clock in a squarish shape, though ideally it's not, but it is not something similar to signal where the fall time is much higher than the rise time. At least it should have similar rise and fall time. Okay. Then adding false path and multi-cycle path and various other timing constraints. Please go through the synthesis slides to go through this again. And we will also set max transition, max capacitance, max fan-out limits on the clock. Once these rules and constraints are set, there is one specific rule which is very necessary and interesting to learn is we put some decoupling capacitors around the clock buffers to save on power. So how does it help to save on power? We are just putting it beside the clock buffer. So what will happen is, let's say this is the clock buffer. Okay, I'm just putting that decap cell next to it. What is decap cell is nothing but a charged capacitor. Okay, this works as nothing. It has various, there are different types of it, but which type you want to use in your design is been decided during the library characterization and all. Now, but it actually works as a decoupling capacitor. It's a capacitor. So what it does is, in normal scenario, this capacitor stays fully charged because this power ground is it's connected to VDD and ground. So this one is definitely fully charged. Now, in case something happens to this clock buffer's power supply, let's say something happened and instead of VDD, okay, that power grid noise came and the VDD fell down to some lower level of VDD and the ground had a ground bounce. So whatever the drop in VDD, right, it's called voltage droop, and whatever the bounce you see over here is called ground bounce. If that happens because of the noise margin of the CMOS, my whole clock buffer can act adversely. It cannot even have a proper output. Sometimes what happens is it gives weird output over here, or it just stays in high impedance stage. So at that point of time, this decoupling capacitor comes to help. What it does is it sees that, okay, the voltage differential between these is dropping. It's not actual VDD. And then it starts charging the voltage supply for this clock buffer. And that is how the clock buffer is saved from any kind of power supply noise. So this is very helpful while deciding the clock tree synthesis. Okay, now let's go and talk about the actual steps of clock tree synthesis. Our rules are set, our objects are set, our constraints are set. We have told the tool our targets also, that this is the skew target, this is the latency target. Now, what actually happens when the tool goes ahead and does the synthesis of clock tree? So the first thing which it will do is, based on the clock tree chosen, we'll talk about this. There are multiple types of clock tree, and which kind of clock tree is good for your design, that you will have to choose. Once you have done that, yes. Does anybody have any question? Okay. So based on the clock tree chosen, the tool divides the tree into two networks, the global network and the local network. And then it does the synthesis of that differently. We will see how it does that. Now, tool performs the global clock routing first, uses the RC estimation to determine all the clock nets and the timing. Then now the tool, what it does is it says that, okay, I have done the global clock routing. I know these are the delay values. Let me start propagating the clock. Now it actually propagates the clock through that wires and performs the final detailed routing for the clock tree. The detailed routing part is from these big wires or the clock buffers to the final clock pins of the clock. Okay. And the fourth part, what it does is it further optimizes the design for timing. It fixes if there are any design rule violations, such as max cap, max cran, and max fan out. It checks whether the clock is not taking much area and tries to balance it. It checks on power, it checks on routability, and it fixes all these issues after actual synthesis. It does this optimization and fixes it. Now, how does the tool optimize the design? It does that, but how? What it does is whenever it sees that the clock tree is not really ideal in terms of timing, it rips out that clock net and says to the tool that I want to route my net in the higher metal layers. So what it does is layer optimization for longer and critical nets. Then the second thing which it does is clock tree optimization, the overall optimization between area, power, and timing. And also there is one concept in clock tree synthesis which we will go through, is called concurrent clock and data optimization. Not only clock, but it also goes through data optimization. So it does both the optimization together to fix the issues. Now the second thing is it splits the clock cell and the clock gating cell based on the max cap. If it is saying that, okay, my clock buffers are driving 25 loads, it is not able to, then it divides that buffer into two. One of them drives 12 and one of them drives 13, like that. And it also does the area and power recovery by swapping the cells. We had talked about this in the synthesis. Can anybody tell me what's the difference between resizing and reswapping? Okay, so the resizing is when you change the drive strength of the cell from D2 to D4, D4 to D6, something like that. And the swapping of the cells is changing the VT type, which actually helps in power. And if it is helping in power, if it is large enough, it will take up an area. If it's small, it's going to save your area. So it does it by swapping the cells. Okay, now let's talk about how many different types of clock trees usually are there in the standard designs. Okay, there are many more ways of doing the clock tree synthesis. These three are the basic types of clock trees. This is called H tree, where what happens over here is, let's say this is your design border. My clock port was somewhere over here. So from here, I will take the clock to the center of the design first. And from that, I'll start splitting it into H. You see this H's? That means that it is trying to balance the delay for all. From this point to this point, how many buffers are there? 1, 2, 3, 4, 5, 6. And to this point also, there are 1, 2, 3, 4, 5, and 6. So it actually tries to balance the skew for whole design. So H tree has the maximum skew balancing. Now let's come to the mesh. What happens in mesh is, so you have to understand one point is these are all the global structures. Okay, once it reaches to this point, this is still a clock buffer. This is called clock drop off point. After this point, there will be a conventional detailed routing of clock happening till the clock pins of the flops. The same goes for mesh. Once from the main clock buffer it divides, then what it does is it creates a mesh kind of structure at certain metal layer. Let's say you have routed your clock from M10, M8, M9, M8, then it will create a mesh at M6, M5, and after that these are all intersection where you see, right, all these intersections are going to work as clock drop off point. From there the conventional CTS will happen till the flops. Okay, but there is one drawback over here. This is also very fine balanced for skew and it's very good for timing, but there is some issue over here which we will talk about. Now there comes a spine. This is not really balanced for skew because if you see over here, the clock came to center, then it divided into comb-like structure, all these red buffers. And then from one comb, they created a big spine, and from there it started giving all the clock drop-off points. This is not balanced in skew, but this is pretty much balanced for timing, the power and area. This is using very less power and area. So it has all the trade-offs. You will have to decide which one to go with based on your design requirements. Let's talk about the advantages and disadvantages. So the H tree has low skew, same way mesh has low skew. As I talked about it, the spine has higher skew. But what happens is the H tree has the lowest capacitance, whereas the mesh has the highest capacitance. Why does it have high capacitive load? Is if you see this buffer's load, earlier what was happening is this buffer load were two buffers, very small capacitive load, but this buffer load is this whole mesh area. Even this buffer load is this whole mesh. So this mesh is going to be very power hungry and very loaded design. Okay, this one has medium capacitance. The drawback in H tree is difficult for floor planning. Why? Because in your design, what if I have a big macro sitting over here, big memory sitting over here? How am I going to do this? There are no cells over here. So I am going to put all my H tree over here. There are some cells over here. How will I put my H tree over there? So this kind of tree works only in symmetrical designs. If I have a macro over here and if I have a macro over here, then I can divide some H tree over here. So these works for symmetrical design structures. That's why it has this one drawback. The mesh has a drawback is high capacitance load, high area, high power, but it's very easy to floor plan. You don't have to do anything. Once you have put the mesh, and all the intersections will take care of all the clock tree. Okay, whereas the spine structure has all good things, medium area, medium power, medium floor plan, but it has high skew, so you cannot use it for the designs which are high speed. So you will have to end up using the H tree, but then you have to take care of the floor plan. So you'll go to mesh, but then you will have to deal with the high power and high area. So you will have to balance all these trade-offs. Okay, now in recent technologies, there is one observation is our conventional CTS, even if we don't use any of this structure, even if we do the conventional CTS, it gives us the best results when used with concurrent clock and data optimization, which we are going to talk about. Okay, now my clock tree is built. Now what do? We analyze the results. We had set some targets, right? Skew and latency and all. We want to see whether it actually reached that or not. So we will check the global and skew numbers, and we will see that, okay, whether it has met it or it's badly failing it, then we will have to restart our clock tree synthesis with different set of rules. Then we'll have to check on violations. The clock nets violating maximum transition, maximum capacitance, maximum fan out. All these clock nets have to be ripped out, or they have to be buffered, or you have to split them. Something has to be done to make sure that they are not violating. Then the timing targets. Setup and hold should be clean. Then the clock tree power. Let's say if everything is good, but my clock tree is using so much power that there is nothing left for my signal routing. After I add my signal routing, my design is going to blow up with heat, then this is not allowed. Then you will have to restart the clock tree. Okay. So this was the basic clock tree part till analyzing results. We are now going to talk about some clock concepts. As I talked about clock tree optimization and CCD and useful skew and something like that. Before that, if you have any questions, please ask. Anybody? Okay. I'm going forward. Let's talk about clock tree optimization. So my clock tree was built properly, but then I saw that these are all violating. Maximum transition is violating, skew numbers are not met, setup and hold is violating. So next time when we restart our clock tree synthesis, we want to make sure in mind that the optimization which happens are really strict. Okay, for that, this is the concept called clock tree optimization. What we do is we build the clock tree. Not only earlier what we did was we built the clock tree and then we analyzed the results and saw that okay, this is violating, this has higher power, this net is not good, this net is being driven in lower metal layer, and then we start ripping it out and fixing it and doing something. Instead of that, there is a concept called building a clock tree along with fixing the design rule violations. So you parallelly do both the things. What happens then is it actually builds a clock tree which is very good in terms of max capacitors, max tran, max fan out. Yes, anybody has a question? Okay. It's very good in terms of these three design rules. Okay. Once it is done, then we check timing to fix the setup and hold violations. So here, what we had to do is we had to deal with all this maximum trans capacitance failures also. Here we only have to deal with the timing and power. Okay. Now what happens during this is one good part which happens is while you're fixing this, right, max cap, max tran, and max fan out, you actually end up having a clock tree which is widely balanced in terms of skew. So you have a very less skew to fix with. So now what happens is if it has very less local skew, very less insertion delay, definitely your clock is going to use low power. Okay, it's going to use low area when you have less number of buffers. If it has less peak current, then you are not going to see any IR drop issues. So these way, while building only if you take care of the optimization, the clock tree which is built is going to be much more better than the one we did earlier. Now, how does it take care of that? So what happens is, before this clock tree optimization, if we go through the plain CTS, it's going to do this. Here, if you see is, for these flops, it is using 3x buffer. 3x is drive strength of 3. Here, it's using 2x. But if it's seeing that this net is violating max cap or max tran, then it's definitely gonna upsize the buffer to 3x. Here also it upsized from 4x to 6x. So this is what the clock tree optimization does. This is much better tree than here. Here you will not see such issues like max tran, max cap violations. It will also do the relocation. There is not much change over here if you see. This buffer was very near to flops and maybe the wire length was very small that it was seeing max cap violation. So it started driving it from very far away. It gave this delay value. Okay. Here you will see some kind of level adjustment. Like earlier, these three flops, the blue colored ones, didn't have any buffer after this main buffer. Now, after the clock tree optimization, it understood that okay, this is not good. It's not properly able to drive. Let me add a buffer. So it divided into different chunks where there were already buffers used. Then it does the reconfiguration. Reconfiguration is normally done based on the local skew group. Maybe it saw that the blue colored flops are supposed to be a part of one skew group. So it divided them, kept them all close by, and started driving it through one buffer. This is called reconfiguration. All these are concepts of clock tree optimization. Then there is delay insertion. Here it saw that these all are skew balanced, but it needs some additional delay to make sure that the skew with number which we want is properly added. So sometimes you add a delay, sometimes you remove a buffer, totally remove a buffer, sometimes you add buffer. That all things are part of clock tree optimization. Okay, now let's go ahead and take one example of useful skew and all. Here, let's talk about some, you guys know the launch capture clocks, you guys know how to calculate setup and hold time. So let's be interactive. Take a pen and paper if we want to calculate along with me, and let's do this. Okay, so I'm going to ask questions over here. Everybody is looking at the figure over here. I need all of you to be interactive and answer me, okay?
Yes.
Yeah. So this is first clock, okay? The clock reaching over here has 2 nanoseconds of delay. This is the second flop. Here also it's 2 nanoseconds of delay. The combo delay over here is of 9 nanoseconds. The clock to Q pin delay is 1 nanosecond. The setup time for both the flop is 1 nanosecond and clock period is 10 nanoseconds. Now tell me, what is the skew over here? Can anybody tell me? Okay. The launch is reaching at 2 nanosecond. The capture is reaching at 2 nanosecond. Do you really see the skew?
No.
No. Correct. So here, yeah. So here what happens is Q is 0 PS. Now what is the arrival time? This data arrival time, this is the capture flop, right? The data arrival time, how do you measure? The data transitioning from clock to Q plus the data transitioning through the combo. So the arrival time over here is this 1 nanosecond, this one, the clock to Q plus the combo 9, which is 10 PS, 10 nanoseconds, sorry. Now the required time is the clock period minus the setup time. Before that, the data should arrive, right? So it's 9 nanosecond. The required time over here is 9, but it is reaching at 10. So is it meeting my setup?
No, no, ma'am.
Yeah. So what is happening over here is the setup slack is -1. Okay. Now what do you do in this case? It's not meeting. What do you do in this case? You try to make this combo delay of 8 nanoseconds somehow, right? You do something, you put high strength buffers and drive them faster, make this combo delay of 8 nanosecond and try to meet it. But here comes an important concept of it. While doing clock tree synthesis, it's not going to touch your data path. It's not going to touch your data path. It is going to look at the data path. It is going to understand that the data path has this much delay. I somehow want to meet this timing while building the clock tree. Then what does it do is, that is what is called concurrent clock and data path optimization, where I'm going to tell you about the useful skew. Now you tell me the difference between these two figures. What is the difference? Can anybody tell me the difference?
Second clock is delayed by 4.
Correct. Yes, yes, sir. So what happens over here is now the skew has come into picture. Okay. So what will happen now is, if you see over here is my capture clock is reaching 2 nanoseconds late. Okay. So my skew is positive plus 2 nanoseconds because the capture is reaching after the launch. Now my skew came into picture. Ideally, it's not balanced by skew. The earlier circuit was pretty much balanced for skew. Here it's not balanced, but how is it gonna end up is, if you see my arrival time remains same, 1 plus 9 nanoseconds of combo delay, it's coming over here at 10 nanoseconds. Now what is the required time? My required time will have this additional 2 nanoseconds added because my capture is coming late. I'm using that skew to my advantage. So now the required time, instead of 9 nanoseconds earlier, we didn't have this 2 over there. Instead of 9 nanoseconds, it is 11 nanoseconds. And because of that, my setup slack came plus 1 nanosecond and I met the timing. So that is called useful skew. I'm using that skew to my advantage of meeting the timing paths. This is called concurrent clock and data path optimization. And this is the concept of useful skew. Okay. Does it understand this, or you have questions? Please ask. If this is very useful concept, it's used in the latest technologies, and nobody's going to talk about it when you talk about clock. But if in your interviews and all you talk about this part, if they ask you that, do you know what is CCD, and you will say yes, I can draw and let you know, it's going to be a plus point. Do you guys have any questions? Okay. Then I have a question for you guys. In this case, what will happen to my next path, which is driven by this flop? Now this will become launch and some other flop will become capture. Unnecessary, I delayed this. Okay. And now if my launch is late, instead of, the arrival time of 10, it's gonna be instead of required 11, it's gonna be 9 for the next path. Will it help or will it degrade? I just want that question. Just want that answer. Will it help the next path or will it degrade the next path?
It degrades.
Correct. So what will happen in that case is clock will again have to start balancing the skew. In that case, what it will happen is it will try to pull the capture or try to push it further, but it should not push it that much further that the whole clock tree disturbs. So that is how the tool has to be smart enough to push and pull the clock of launch and capture to make it useful and not degrade the structure. Good enough? So this is where our clock part ends. We'll talk about route now. Please ask if you have any questions, or I'm going to take like 1 or 2 minutes break and we'll start again. Okay, let's go ahead with route. Now, your first synthesis is done. Your floor plan and placement is done. My clock tree is built. I have analyzed the clock tree. It's good in terms of power, area, timing, everything. Now, my signal has to be routed, right? So for that, the routing has to happen. Now for that, these are the stages, some prerequisites, some routing rules and constraints, same way we had clock rules and constraints. Then the actual routing happens and then the optimization. Okay, so these are the prerequisites. What should happen is power grid should be routed. In the routing stage, the power grid should not move. The clock tree synthesis should have happened and the optimization of that clock tree synthesis also should be performed. Then the congestion is within acceptable range. Timing is within acceptable range. So after the clock tree synthesis also, the design is not timing clean yet. It will try to optimize it however much it can, but that does not mean that your setup and hold time will be 0. Why? Because your signals are not really routed until now. It will get routed now. The real delay values will come into picture now. So it will again start degrading. Then your design rule check will happen. max tran, max cap, max fan out should have zero violations. It cannot have any violations once your CTS is built. If it is built, you cannot proceed with routing stage. You have to redo the CTS. Okay. Now, let's define some routing rules and constraints. Some via and via ladder insertion rules has to be formed. Can anybody tell me what is via ladder? Can anybody tell me what is via?
Through it.
Yeah, connect between two metal and metal and metal and non-metal.
Interconnection between two metal layers.
Correct, correct. Now, what happens in via ladder? Let's talk about it so that we know the things better. Okay. Draw over here. Okay. So I'm just drawing a very let's draw it this way. Okay. This is my metal layer, and this is my horizontal metal layer. Let's say these are all the horizontal metal layers. Correct. These intersections are called via. Okay. Now, to attach this via, there will be only one, connection which will be given. That is called one via. But in case, if you see the top structure of the via, it will be something like this. It's nothing between. This is the top part of it, which actually looks like this. Let me show it this way. This is how the via looks. Okay, I'm trying to draw it in the 3D. You guys have to imagine something out of it. Okay, this part is gonna touch the top metal layer, and this is gonna touch the lower metal layer. What happens is, this is just one via, which is this intersection between top metal layer and the lower metal layer, and this is gonna provide the low resistive path between the metal layers. But what happens if the vias in the design are less in numbers and your current is so high that these via wears out? When it wears out, what happens is it starts getting, decayed from here. Okay, and it becomes half of it, or it just is a smaller part of it. And from there also the current is still going through, which is like very high in density, and then your whole via will wear out at certain point of time. So in that case, what we do is we use multiple vias at one intersection like this. This is the top structure which I'm drawing. 3 by 3, 3 by 2, whichever is preferred in your technology, whichever is preferred by the your current carrying capacity. Okay, what happens is it gives multiple paths for the current distribution, and that is the reason it does not wear out easily. That is called via ladder. Via ladders are used when mostly for the signals which are very high in current density, like DFT signals, clock signals, and reset and set signals for the whole design. That is where we will use via ladder. Okay, then same as clock tree, we will also use non-default routing rules for some critical nets. So can you name some critical nets after clock? If there is a flop and data is signal, clock has already reached. Does the flop has any other pins in it? What do you do when your whole design is shut down and then you power on the design? Immediately the clock starts flowing and your flops start working and you start taking the output? Or you try to set the design first at certain Boolean equation? I mean, you set all the flops to 0 or 1, something like that.
Using reset.
Yes, so reset, set, enable pins, clear pins, all these pins are critical. Those all pins have non-default routing rules, same as clock. Not exactly very constrained or high as clock, You might not use double width over there, but you might end up using, double spacing for those nuts, because you want to bring those nuts to the flops in their original signal shape. Integrity should be very close to clocks. So for that also we use non-default routing rules. Now, routing constraints for voltage specific area. There can be a design in which you have two different voltage areas, and both of them will have different set of routing rules. Now, routing blockages to prevent routing over macros and black boxes. So let me ask you one more question. If the standard cells in the design have pins in M2, even the memories will have pins in M2? Or the pins will be in some other layer? If yes, lower or higher? Okay, so let me give you this answer. This macros, right, the memories, it will have a complex structure in it. So it's not possible that the pins of the macros will be at M2 or M3 layer. It will be normally at M5, M6, M7. So that means that on top of that macro, you will not be able to route any signals till M5, M6. Okay, so you'll have to tell the tool that in this area you cannot use the routing resources till M6 or M7. On top of that you can route. These are called blockages to prevent routing. Then, same as blockages, there is an opposite concept called guidance. At some places you want to guide the tool that, okay, these are the critical nets, let's say set and reset. Please prefer some metal layers for those kind of nets because you want to route them in higher layer, or you want to control over the density of the routing because that is high congested area. Between two macros there is only a channel where you see a long horizontal channel, so you want to tell the tool that use only horizontal resources, don't use vertical ones. All this is called routing guidances. Then routing groups. The groups are actually same as queue groups for clocks. The way we told clocks that you have to divide flops into chunks and you have to balance queue for them into chunks, same way for critical nets also we define clock route groups, which means that you have to route these groups before you route any of the nets nearby. So these are called route groups. Now the actual routing will start happening. What is it? It is also in terms of stages same as clock, global clock, detailed clock. Same way here also the routing is in terms of different structures. First is global routing. What it will do is the tool will divide the whole block into small cells. Let's say if my design is 100 by 100, it will divide it into 10 by 10 small cells. Okay, which is called global routing cell or G cell. Then it will decide that, okay, inside each cell these many cells are sitting, so I'll need these many horizontal or vertical routing resources, and let me calculate how many routing resources are actually available. Okay, so here if you see, this is called overflow. Whenever the tool sees that, okay, the actual routing resources available are less than what I need, it reports overflow, that I am not seeing enough routing resources over here. You are going to end up in routing congestion. That is called global route congestion. Now there is a utility in the tool for in each and every tool where it will call that global route congestion map, in which the user can see actually that, okay, this is the space where it is shown red in color. That means it does not have enough routing resources, and what user has to do is it has to provide more area or space. Now it also tries to balance the timing, noise, SI. It also tries to minimize the wire length. All this is a part of global routing. Once it is all done, the actual routing has not happened yet. It is just an estimation. Now what happens is, now the tool goes ahead and asks the metal tracks to assign all the nets. That okay, this metal 7, I'm giving it to this clock. The metal 8, which is horizontal, this much part, I'm giving it to this signal. This part, I'm giving it to reset signal. That is how it starts assigning it to the actual nets. Then the detail routing happens. Now detail routing, what happens in detail routing is, after it analyzes all the tracks, it starts assigning them and actually routing them in the design. So the global routing connections were logical, whereas the detail routing physically connects the net with different metal layers. Again, what it does is it analyzes shorts, open, then it analyzes max cap, max tran. Every time, every stage will keep on analyzing all the design rule violations and it will try to fix it. If it sees any open nets and all, what it will do is it will rip the net out and reroute again after fixing the violations. Once this is all done, your whole design is set. What it does is it goes back to the first global routing set again and starts searching for the violations. It is called search and repair. Search for the violation. If you find a violation, repair it. It fixes all the remaining DRC violations. Until this point, clear to everybody? Any questions? Okay, now let's talk about this DRC. Okay, this is, I have just given you a blog. If you get more idea of it, how global routing and detailed routing happens. See, these are the small red lines. If you see, these are all G cells. Okay, in that, let's say one net has to be routed from here to here. So what global routing did was, it said that okay, for that net, these are all the routing available, vertical and horizontal resources which are available. It just kept aside for that net, that you can use these many routing resources. Now when the detailed routing happened, it actually started routing it in one of the assigned metal tracks and it started using it. What will happen now is, this rest of the area, right, will be used by the second signal. So this is how it does. It assigns and then it actually routes. This is global routing, this is detailed routing. Okay, now once the routing is done, what it is doing to optimize, and what are the post-route checks. So what it does is, it checks the legality of the cells. We know that the after placement, the cells are not allowed to be moved, but what if while fixing routing issues, it actually moved? So we check the legality of the design again. We check the routes. There shouldn't be any opens or shorts in the routes, because that actually means that there is something logically incorrect. Then it does the delay optimization. It does the RC extractions. You take a wire, you do the RC extraction, that will give you the delay value of that wire. And how will it help? It will give you the final delays of that net. Now your timing will again start to violate. You will have to again fix it. Then it also updates power, performance, area results based on all these final latencies, which is the real-time latency. Then it optimizes that. Anything which it sees that got violated, it has to refix that. What it does is, in that case, it achieves area power recovery, reduces noise. But one has to make sure that the tool will not be able to recover or refix all the violations. There will be a whole bunch of things left to us to fix. And then finally, it will do the ECO routing for hold fixes and EM fixes. Anybody has questions until now? Okay. So this is the DRC, design rule check. What happens is, this is how the open looks. When you have two nets routed next to each other, and if there is a cut between that, this is called open. And if there is the two routes are touching each other, it is called a short. This definitely is a no-no. Okay. Now, these are some DRC violations. If you see over here that this DRC violation says that, okay, you cannot have a via very close to a vertical layer. So what it does is, you basically cannot have a notch. So it, moves the via like this. Then it tells that you cannot have two vias with this much spacing close by. So what it does is, it says that, okay, I don't want to have notch, so I'm just going to traverse my net like this. Then this is one of the design rule violation where it says that if your metal width is this much wider, this small space is not allowed. Then you need more space, then it will space out. Same way, two vias cannot be there nearby with this much of space, so it will just move one via above, one via down. It will create more space between that. These are all design rule violations based on your technology norms. Okay, let's talk about two fixes which are done post route. These are the final fixes for the design. One is called EM fix, one is called hold fix. Can anybody tell me what is EM, the full form of EM?
Electromigration.
Yes. Now, what happens when electromigration happens in a wire? So what happens in a wire is, whenever you have a current, okay, which is in one direction, it's always traversing like this, let's say. Along with the electrons, what will happen is, the atom, right, of the metal wires will get struck, and because of that, the atoms will start moving. Two things can happen when the electromigration happen is, it will start moving and start creating a bad net over here after few years. This is when the wear out happens of the chip. This is reliability testing. Okay, what happens is, after few years, it will have a open over here, the whole thing will wear out. And the other thing which can happen is, if it starts wearing out too much that it touches some other metal layer, then it's going to create a short. So these are the issues when EM happens. So what happens, how to fix that? So normally what this post route check does is, the EM is totally based on temperature, wire size and wire material. So what it does is, it widens this wire, it puts a bigger size between that so that it doesn't touch after few years also. It widens this wire that even if it wears out, it does not totally become an open. There is some part of it still left, and that is how it resolves the EM fixes from now onwards. Or what it does is, it does the driver cell, right? The driver cell of this net, it actually changes that to higher drive strength or the lower drive strength, possibly lower drive strength, so that your current capacity becomes lower and it does not drive a very high current, and the wire should not go through EM. Okay. Now we have gone through setup and hold one time. This is the final question. Can anybody tell me that, can a chip tape out with hold violations? Have you seen a design where you have heard that, okay, it has some one piece of hold violation left in the design and we are going to tape it out? Does that happen? Okay. Can it tape out with setup violations? Yesterday in the DFT session, yes, somebody has the answer.
Yeah, the chip may not work.
Correct. And what happens if I tape it out with setup violations? I will not have hold violations, but what if I tape out with setup?
There may be delays.
Correct. So yesterday we saw, right, in the DFT session, that you are not supposed to throw out the chips which are not exactly working at 1.5 gigahertz if that is what is meant to. What you do is, if few of the chips are not working at 1.5 gigahertz, which it was meant to, then you put them aside, you test them out, and you see that okay, it's at least working at 1.2 gigahertz. Then you ship them or sell them saying that these are the chips working at 1.2 gigahertz. So you can actually tape out with setup violations. Chip cannot be taped out with hold violations, but chip can be taped out with setup violation. What we will tell is we will reduce the weak frequency and we will sell it out saying that it is lower. Okay. Now, when we say that chip cannot tape out with hold violations, we have to fix it. And the tool has to help us fix it because hold violations are very tough to fix. Do you know why? Does anybody had a reason of why? How do you fix setup violations? You touch data, you touch clock. We saw, right, useful skew. I added skew and my setup got fixed. But can I do that to fix hold? So this is how the tool fixes it. It decreases the capture clock latency or increases the launch clock latency based on what it sees in the design, because later on there is no way you can touch the clock. Okay. Increases the data path delay, adds a buffer or reduces the drive strength of the buffer. Reducing drive strength will always increase the delay. Okay, so that will help adding more data path delay and the hold will be fixed. And after all this is done, right, once the route is done, EM fixes are done, hold fixes are done, it again does one more round of design rule violation fixes. That is where the routing ends. Okay. The tools used for routing and CTS are Synopsys IC compiler, Fusion compiler, Cadence Innovus. And after the routing is done, the next stages are layout verification, then generating GDS files, which are graphic data stream, which is nothing but a mask for fabrication, which you will send out to labs. Then you do layout versus schematic check once more. You do the reliability verification, and finally the fabrication happens. This is where your VLSI design flow ends. And then there is this final physical verification which happens, and then it fabricates. So this is the end. Any questions over here? I've added all the references of the material which you can use to understanding electromigration. Then there are some files to understand timing paths, clock tree optimization. Please go through it. And that's it from my side. Please ask questions if you have.
Participants, if you are having any questions, you can ask to the madam. Madam is with us. Up to now, there isn't any question in the chat box, madam. So let us wait for a few minutes if participants have any doubts.
Sure.
Industry is using this clock gating optimization and all. Is there any usage of power gating?
Yes. So whenever clock gating happens, it's actually meant for power gating. Okay, because clock is like huge power hungry signal, right? Whenever you are actually gating the clock, it's actually saving up your power. It's a power getting method only. Just that you are getting the signal which is called a clock, so you call it as clock gate, but it's a power gating strategy. So whenever you gate the clock, whenever your enable signal is 0, the clock is not transitioning. That means you are not using power after that at all. There is no dynamic power consumption happening after that. It's actually saving a lot of power.
Anyone else?
I have one more question regarding this. Just to work on this clock optimization, Which free or open source can I have?
Again, I think I will send out that link again. The open source tool which I am aware of has all this utilities already existing in it, but I'll have to check. I'll send out the link.
I would request participants who are asking the questions that after completing your question, please put your mic turned off so that the echoes can be avoided. Okay. Any other participant wants to ask anything? Mr. Monas, for appreciating the presentation. Yes, sir.
Hello, sir.
Good afternoon.
Mansi, how are you?
I'm good, sir. How about you?
Yes, very much fine.
Yes.
So today, many students are asking that which one is better, physical design is better or verification is better, testing is better. So, in your opinion, which one is better?
Sir, I would say it's all depending on their interest. I was very much interested in design, and that's why I had carved my career in certain way that I'd ended up in physical design specifically. There are subdivision in design itself. I mean, RTL design, circuit design, physical design. So even if somebody is, we all know that testing and verification is 70% part of the industry, but that does not mean that design is not vast enough. Design has so much career growth in it. After you do the designing, if somebody has a dream of ending up in a fabrication unit someday, if you want to work on the labs in the fabrication unit in US and all, then the design is pretty much the way of doing that. Whereas testing and verification, I would say that is huge industry that also gives both has the pros and cons of it. Design has, somebody say that design has more economic growth also, but that's not true. Even verification gives that. Both has its pros and cons, but it's all depending on interest. Verification
and sometimes
will have
students are also asking, like, you say after 5 to 6 years, I want to change, totally. I want to from VLSI to communication, let's say. Is it possible, or after that it's not possible?
I would say changing jumping such a big gap, that is not possible. But if you are in VLSI and you want to change from testing to verification, or verification to design, or even in design from physical to circuit design, that is possible, definitely. Yes.
So nice to listen to you today. I mean, in your company, what type of work you are doing? The same thing, I mean, physical design.
So yes, I am doing physical design, whole physical design. It starts, good part being in Intel is outside industry is called physical design only after synthesis happens. Whereas in our team and in our group, what happens is as soon as the RTL is written, it comes to us. And we will do the synthesis ourselves, and we will take it till we tape out the mask to fabrication unit. So that is how I'm enjoying it a lot. It's not just design, it's everything.
And whatever going on at present in curriculum is okay, fine, or is any modification is required? Because we are offering two subjects. One is VLSI design, and one more we are offering this time is verification and testing also we are offering.
Yes.
So I think Koringa sir will send you the syllabus curriculum, and if there are any changes if you want to recommend, you can go through the syllabus, and then if some changes are required, you can.
Definitely, sir. Definitely. I have some inputs over there. We need to have a thorough VLSI design course, as you said, and definitely a separate verification course, because there there is no point in learning, very small part of design and not at all verification when the industry has 70% built of verification. So we need to have that. Yeah.
Okay, thank you all. Thank you very much, Mansi, for joining
you,
with
sir.
us today.
Yes, sir.
Your last session I missed. Actually, I wanted to attend, but there was
Yes,
my
sir.
lecture also at the same time. So I couldn't
Oh,
attend.
okay. Yes, sir. It's my pleasure. I was like giving it back to the things which I've learned from. So yeah.
Madam, there is one question in the chat box that why good companies prefer only tier 1 college students. What about tier 2 and tier 3 students if they want to enter in the good companies?
Okay. I think, see, I will say that it's not true that tier 2 and 3 students never enter into good companies. Maybe later, maybe at some point, maybe 2 or 3 years late, but it's not true that they will not end up in good companies. I have had friends when I did my masters. What they did was they came to Bangalore along with me, okay, and they studied in some this training institutes which specifically focus on growing your career or your skills at the industry levels. So if you do that, if you don't want to do an MTech, and if you are not ending up in a good college, then you definitely do that, go through a training institute which will carve your skill set in certain way that you definitely will end up in a good companies. It's not true that tier 2 or 3 colleges students will not end up in good companies. There are paths available and it will happen.
Okay, any other participants? If you want to discuss with Madam about anything else.
I would like to say, sir, this thing, I mean, the way we are doing this FDP, right? I think it will be very, very useful. I mean, if
Yes.
this level of in-depth knowledge, if we are able to provide right now, then it's going to be very useful to the students, to the faculties itself, to know how industries work, and that will itself help them crack the interviews.
Yes, definitely, ma'am.
Yes.
That is actually the main intention behind arranging this type of training program.
Yes, sir. And one of my hope is someday I want to just have to be able to collect all the interview guides which can help students to read and crack the entry level interviews itself. So if
Okay.
we can do that,
Sure.
that would be a good thing. Yeah.
We would be trying to arrange that also, ma'am, in future.
Sure, definitely.
Okay.
Yes, that will be a part of it.
Anyone else? I think not much questioning is there. So, so let us conclude the session over here.
Sure, sir.
On behalf of the department, Electronics and Communication Department, GEC Rajkot, I would like to thank you again, Madam, for spending the maximum time available with you for us.
Yes.
And it's your second session with us. So we are really glad to have your expertise to be shared with all the participants.
Thank you
Thank
so
you
much.
very much.
Thank you, sir. Yeah. Thank you.